Thank you, Pat. Thanks. Okay, so some people find it cool to ride a motorcycle or to say that you speak 7, 8 languages. What I find cool is this fascinating world of technology that we live in. I mean, think about it. We're standing here and we're talking about additive manufacturing, drones, sensors, robots, artificial intelligence, and we all pretend that that is something normal. Technology is moving so fast, we cannot even catch it, we cannot even understand it. So today I wanted to talk to you about some of the technological trends, get a little bit a deeper dive of what Pat was talking about, and tell you about them, what they are, why should you care, and what are we in Autodesk doing about them. We are on the verge of a revolution. It's a technological, social, and cultural revolution, and it's called infinite computing. Infinite computing is the confluence of 3 trends: the exponential rise of computing power, the democratized access to that power, and the precipitous fall of the cost of that power. So if you combine these 3 trends with the cloud, then what you're looking at is being able to deploy hundreds or tens of thousands of computers at one problem, at problems that you, as designers and architects, need to solve today. So let's take a look at that. Imagine you have a problem, and you give it to one computer to solve it. The computer will solve this problem in, let's say, 10,000 seconds, and it will cost a certain amount of money. With infinite computing, you can give that same one problem to 10,000 computers at the same time. And they will solve it in 1 second. And guess what? For the same amount of money. Being able to apply infinite number of resources to solve a problem for the same amount of money at no additional cost, it's a first in the history of humankind. And this will change forever the way we live, and definitely the way we design and make things. So when computation was finite, when we were designing traditionally, it was us, we, the designers and the engineers, who were directing the tool. We were telling the tool what to do, and we were deciding when we will call simulation to see if our designs are good. So if I were to design this car seat, what do I do today? I design it explicitly, telling the computer what to do, and then I decide to call a simulation to get a feedback on my design. The simulation will last about 7, 8, 10 hours, and then I get feedback and I see, oh my God, there where the red color is, probably my seat will crack. So I will need to redesign and start to add a little bit more material. That will add weight. It will make the gas mileage not so great. Then I analyze again, I get the feedback, and it goes on and on. Not very efficient process. With infinite computing, we can flip that around. Instead of analyzing, or what we say, proposing and disposing designs and analyzing one at a time, what we can do is analyze many solutions at the same time, simultaneously, concurrently. And that is the promise of the infinite computing, because it can mutate and generate thousands of options at the same time, and you can analyze them simultaneously. Welcome to generative design. What generative design is a method of designing where you, as a designer, as an engineer, as an architect, can tell the computer your goals. You're defining, let's say your goal is a certain style, a certain material, a weight, a cost. Basically, think about any criteria that describes a problem. And then the computer, taking the infinite computing as a basis and some smart algorithms that are usually partially based on evolutionary patterns in nature, will start calculating different variations. Basically, it will start expanding the solution space. So, in the age of infinite computing, with generative design, we will no longer simulate based on a finished design, nor we will simulate during design, which is great and useful, but we will use simulation to discover design, to discover the solution space and see everything that is possible. And not only this type of design will reduce the material cost, the time to production cost, it will look cool. The point is that this also will offer us solutions that we never thought of ourselves. It augments our creativity. For years, we've been working with Airbus. Airbus is looking at the future of flying and thinking, how can it make flying more affordable? How can it make more sustainable and more experiential, more beautiful? So you have already seen this exercise. We basically tested the first generative algorithms on this. We wanted to use this partition wall that usually is very heavy and try to see, can we make it lighter? Because when it's lighter, what does that mean? It uses less material, makes the airplane lighter. That means it uses less fuel, and the tickets will be cheaper, right? So we applied a generative approach to this partition wall, and we wanted to make it lighter, but not compromise on the sturdiness, on the structure of the partition, because it still has to hold the stewardess seat. After reviewing tens of thousands of options, we arrived to a partition that today uses only 1/3 of the material that the normal partition did, and you already are probably flying with some of the airplanes that already have that partition. We continued working with Airbus, and we are now co-designing a frame for the seat. And just imagine this. If all the seats on the airplane would be exchanged with this lighter frame, what would that mean? The big airplane can be now 1/2 a ton less heavy, 1/2 a ton. And then that would translate in about 200 tons less carbon emission. So these are amazing numbers. But what's interesting about both of these cases is this. Only when we physically produced, when we 3D printed the partitions, the seat, did we discover how complex they are, how incapable we are as human beings to understand if it will fail. But a computer can. So while we could hold this in our hands, we could not hold it in our heads. We're not good at this, but computers are. So our structures that once used to be so simple and understandable, inspectable, today become inscrutable, unbelievably complicated and difficult to understand. Now you will say, oh, that's cool, generative design, when you make products, industrial designs, that's fine. But what about architecture? Architecture is so infinitely complex, and there's so many stakeholders. How would you even think of applying such a principle to architecture? Well, you're right, it's complicated, but we did take upon that challenge. And actually, we had a great opportunity. Our Toronto office was moving to a new headquarters, to new quarters. And we thought, how about using this as a living experiment to apply generative design approach and design a space that can be optimal for the people who will use it. So how did we do that? Number one, we interviewed our employees. We asked everybody, how do you want to work? Where do you want to sit? Who do you want to sit next to? Do you want to sit next to the kitchen? Do you want to look outside? Do you want to hide in a corner? So basically trying to understand their preferences. And then we defined the goals. When you define a goal, it's super important that it is a measurable goal. So then the system evaluated the survey that we took from the employees against the hard constraints of the building, because the building was already built, and we knew where the kitchen area are, where the corridors are, so there were some hard constraints. And then we let the animal go. Basically, the algorithm started to work. And they started to evaluate all of these criteria that our human brains cannot do at the same time. I can't think of this and this and this and that at the same time, right? So the system was running and creating tens of thousands of options, and then displaying them in a form that once it was done, every colored dot, I could understand how was it calculated and what criteria were used, so that then I can understand the trade-offs and see, okay, if I want this to move here, then it costs me there. This is the magic of generative design, of automation applied to generative thinking. We believe that we designed something that our colleagues in Toronto like, and if they don't, the system is such that we can very easily recalculate, or if there are new people coming, we can again redistribute and ask the system to work. What's important here is that in our traditional design, our tools were waiting for our instructions. They were sitting like this and waiting. If we don't move the mouse, nothing happens. Here, instead of that directive approach, the system, the tools become adaptive. They anticipate our needs. They start understanding what we want. Now, when talking about the generative design, when we use generative design, we create shapes that are almost impossible to produce with current tools of manufacturing. So how do we make them? It is thanks to additive manufacturing that we can at all produce those shapes. So let's talk about additive manufacturing, or as we call it popularly, 3D printing. Unlike subtractive method, where you take a block of material and you start carving, subtracting until you arrive to the shape, in additive you add. You only drop droplets of material following the recipe of the geometrical shape, build it up, until you get the shape that was needed. What's important here is, number one, we only use as much material as we need it. There is no waste. Number two, complexity comes for free with 3D printing. A 3D printer, an additive machine, doesn't care less if it's a straight box, or if it is this crazy shape that is otherwise non-producible. It just goes left, right, up, and down, and builds it up. And it doesn't need any mold, any cast. The third thing is that additive machines can use many, many different materials. Individually, or in one machine, you can put different types of materials. The future of additive is actually in new materials, and we're looking at developing and understanding what does it mean? How can we leverage this process even better? The fourth thing about additive is the fact that you can print entire assemblies in one go. This might be made out of 20 parts, but we didn't print the 20 parts separately and then assemble them. We printed it in one go. If you designed it to have a tolerance and work, it will work when it's printed as well. Think about what this means for assembly lines. Maybe in the future we will not have any assembly line. And another thing is that one machine can print many different materials. And every single droplet of the 3D printer can be different density, different property of material, different color, etc. How do we design for that? Our design tools today are not necessarily ready to design on that micro level and be able to do that. So given all of these unbelievable qualities of additive manufacturing, what do we do in Autodesk about it? We are determined to become leaders in design, simulation, and automation of advanced materials. We're developing expertise on polymers, on carbon fibers. We're looking at in-process inspection, at adaptive machining, etc. So we make tools that today can take any design and not only prepare it for 3D printing or additive, but also optimize it, and also simulate the printing part of the printing of the part before we actually do it. Because, for example, metal printing is very expensive. You don't want to print and only then see that something will fail. So you want to simulate and see. I also said that we can make designs where every droplet is different. Imagine I'm designing a prosthetic cover and I want here to be flexible, here to be hard. How do I design that? So we're looking at voxel-based approaches to design where we can use topology optimization also for material distribution, so that we can make materials that have non-linear, non-uniform qualities. And we can design interesting things like this table here that is beautiful and practical. 3D printing is slow, it's expensive, and it prints small parts. We want to make it fast, affordable, and print large parts. So here is Project Asher. What we do with Project Asher is trying to create an OEM software where you can basically tell multiple tools to collaborate between each other and create something bigger. So here it is. Usually a 3D printer will have one print head and print. Here we can give it as many print heads as we want, and they will start collaborating and making big parts, and faster and cheaper. And guess what? This is not only for additive. This does not need to mean that you have to only use printing. We can combine subtractive tools and additive tools and let them work in parallel, because the future of manufacturing is not just additive, is not just subtractive, it's both. So, 3D printing, from nanoscale to city level, we will be seeing it in the future everywhere. We'll be able to print DNA. We're already able to print some parts of the human body. We can print replacements for fractured bones. We can print bespoke prosthetic covers. Nacho would love to see this. We can print food, and even a food that has her face scanned on it. We can print fashion. We have customers who already started to do the first printed cars, the first printed buildings. This is a $5,000 house, and it can be built in 10 hours. For low-cost houses, this is amazing. And there are already companies who are making the first robots that can print buildings. You can rent this robot, and you can start printing a building. Now, Pat said something else that was magical, the word sensors. We live in an age of sensors. And these sensors can help us do lots of things. Laser scanners, for example, can help us digitize the analog world around us to put it in the computer, to bring it inside, so that we can create something like this that is a point cloud, something that was never designed, never 3D modeled, and it looks like real. Why is this useful? Well, we usually start designs from zero. And why would we start from a blank screen when we can start in context? But we can use this to follow progress on construction site, to do factory retrofit, et cetera, et cetera. And here is one of our tools for handling point clouds. It's Recap. We can visualize the point cloud in many different forms. We can prepare it for downstream application. We made the process of registering the scans automated, so it's all becoming easier and lighter to work with the reality around us. What I love a lot is the process of photogrammetry. This is creating 3D high-definition models from simple photos. You take a bunch of photos of an object or of a landscape, and the software automatically converts that into a 3D digital model that looks awesome. Now, could you model this with 3ds Max or Maya? Sure, but you need to be an expert. It will take you a couple of weeks, and it will never be the digital replica of that object. It will be an interpretation. This is the real replica of that object. And as if that was not enough, we also live in the age of drones. This is not working. Okay. We live in an age of drones where drones are becoming so cheap that for $1,500 you can buy a drone with a high-definition camera in it, and you can start flying and capturing the landscape, again, as a start of a design, or to follow change on a construction site, or you're planning your building site and you want to see how much excavation do you need to do, et cetera, et cetera. All of these technologies are not only interesting when we build new things, but they're opportunity to also save our cultural heritage, because we lose our heritage on a daily basis because of tsunamis and earthquakes and acidic rains and wars and terrorist attacks. The government of Rajasthan is one of the first pioneers in this area in the region. They realized the opportunity of these technologies to digitize their beautiful heritage, but they also, marching toward the concept of smart city, want to use them, make them smart, and also by IoT and sensors to follow how they're behaving, but also use them when they plan around these buildings in the new city. And those very same technologies are used by museums. This is the Smithsonian Museum, the biggest collection of museums in the world. They have about 154 million objects, and yet only 1% of those objects is in museums. So they wanted to give access to all the people in the world who will come or not come to the museums to see the beautiful things that we have in those museums. So using this technology, they started digitizing their artifacts, and we help them also build a beautiful explorer that works in browser, where you can see the objects, explore them on your own. The curators can tell you the story of their objects in a 21st century way. A teacher can ask the kids to just open the mammoth and see how tall was the leg instead of learning from books. Education starts to become experiential. And then the last project we did with the Smithsonian was the digitization of the historic Apollo 11. So today, you can actually sit in the Apollo 11 without having to be one of the astronauts who were in it, and experience what it meant to be one of those brave 3 guys who landed on the moon. But sensors are smarter than just capturing the geometry. They can capture so much more. Today we have sensors that cost almost nothing, and they can follow humidity and light and occupancy and temperature, etc. So very early on, when the world started talking about sensors and IoT, we actually completely sensorized one of our own offices. And the idea was to take an old building and make it smart, give it a voice, give it an opportunity to tell us back how is it doing, make that building a living building. So this alive building is now showing itself in this interactive building performance visualization tool that is called Project Dasher. And the idea is that you can real-time see how your building is performing. Where do you lose temperature? Well, can you explain those hot and cold calls, etc.? This is a connection between BIM and managing your asset and taking a look actually also as an architect. Did they design it well? So if we have this feedback from the objects that we design, that feedback we can take in the future and design better. But also for the performance of the building, this can be very, very useful. One cannot talk about the future without talking about robots, right? And robots are nothing new. They have been used industrial robots have been used for a long time. They're incredibly smart machines. They're versatile. They can do so many things we cannot do. But they have one problem. They have to always have an expert to talk to them, to change them, to calibrate them. So if this was your assembly line and you need to calibrate these robots, it will take you almost a year to recalibrate them. In that year, this line will be stopped. The other problem is because they're heavy and strong and scary, we keep them confined in a little prison. We need to be safe from them, and everything that they work on needs to be kind of hard-coded. That part always has to be here, the robot always has to be here, etc. So this is very limiting. It's time-consuming, it costs money. The robots are becoming cheaper today, and we want to find a way to make them talk to us in an easier way, and also make them be a little bit freer. We don't want to keep them as slaves. We want them to understand what we want, and then they do it. These are our first efforts to talk to a robot and just ask him to follow our gestures in order to move their own hands. Our previous CEO, Carl Bass, came one day to the team and said, okay, you guys, don't tell me that I have to draw in CAD a rectangle in order to tell this robot to cut a rectangular shape in the wall. So what we did here is we took a small robot, we put a web camera, we put a projector and a router, and with voice control and few gestures that we trained the robot, we just told him, okay, I want to drill here, here, and in this shape. And the robot says, okay, and it starts doing that. These are our first efforts to see, can we find a better collaborative way and language with our robots? Now, this guy is something else. This is a robot called Ash. It's huge and scary, but we don't keep him confined in a box. Actually, we wanted to give Ash the full freedom to do something that we will tell him to do without our further instructions, that it anticipates after we said and has the complete self-control to do it. So we made Ash to become a metal 3D printer. We put a MIG welder on it. We gave Ash eyes. And the idea was that Ash was given the instruction and now started to print, in this case, the chair. But what's important is we gave him eyes because we wanted Ash to understand if when it prints the way it's supposed to, and if it makes a mistake, it self-corrects. It learns on its own, and it becomes better and better. This is the magic of these closed-loop systems, and systems that learn on their own, and they become better and better. And Ash made the chair that we designed previously with the generative design. There is something else as well. While we're adding more functionality to Ash, we also wanted to make the language, the way we collaborate with him, a little bit easier. In this case, we brought Ash in a full virtual environment, and that allows us to step in his world. And now we can use our controller to actually control Ash in the virtual space, thus understanding if it will crash something, if there are any obstacles, but also not be close to him when it's sparkling that molten metal that it was building the chair from before. The last project that we did with robots is very interesting. This is Bishop. This is another robot. And we introduced Bishop to the very disorderly world of Lego. We wanted Bishop to understand what are Lego bricks and how to assemble it on its own. So we gave Bishop eyes, and we gave Bishop a hand. And after a while, Bishop understood that he can see, he can grab, and he can start assembling. But we wanted to train him faster. So how do you train him faster? You can either let Bishop for the next 3 years do that until it learns to do this fast, or you can do hundreds of Bishops next to each other. That costs money. So instead of having a lot of robots, or one robot doing it in a long time until it learns, we introduced an artificial world for Bishop in which he can start learning and learning much faster. By decoupling this learning environment, making it artificial, from the real world, we actually decoupled time. And now, Bishop is learning on its own in this artificial world where we feed a neural network images of the Legos that almost similar to what he sees in real life, but we created renderings of simulated images of the Lego, and now he's learning in computer time and learning much faster. So we built a machine with curiosity, and then we let intelligence evolve. And it's fascinating to see and to follow how much better he becomes. The thing is, once you teach one robot to do this with the cloud, you have taught all the robots to do it. And once they know how to do it with a Lego, they can do it with any object. And once I add another Lego block, he's not confused anymore. He understands what my goal was, and it doesn't matter that the conditions changed. He's still going to do the same thing. Machine learning is unbelievably potential, and we're just scratching the surface of that. With machine learning, we can save people's lives today. We can save endangered species. You're exposed to machine learning already without knowing. Every time you're translating something on Google, that's machine learning. Every time you're typing and it auto-completes a word, that's machine learning. Every time you're buying a book or watching a movie, what's suggested to you, again, is a machine learning system that is just transparently embedded in the services. Machine learning can be also useful in construction. The construction industry, we all know, it's low margin, high risk. It has lots of stakeholders, and it's very, very messy. And the risks are usually on job site. It can happen on any project at any given time to have about 10,000 issues. How is a superintendent, a poor human being, going to understand what of those issues are important, what are urgent, and how to escalate those to be higher than the others? Welcome to BIM 360 IQ. This is the solution for that. Real data from construction sites is at the center of BIM 360 IQ. And what it does is, we have gathered about 24 million documents from 10 years of BIM field data and trained the machine learning system to understand from that historic data what issues were important, what were okay to wait, what are water issues, how urgent are they. So today, a superintendent can look at BIM IQ just like it's looking at a weather prognosis and can see already a system that helps him elevate the important and urgent issues, and out of 10,000, it will say, you have to deal with this 30 today, and 5 are water leaks, so you have to deal with that as well. And also, it helps us understand about our subcontractors. Maybe some subcontractors are not that good, and the historic data will show that, so maybe we'll not hire them the next time. So this is really like a smart assistant that have many more brains than your one brain that helps you do your job better. We started just by analyzing historic data, but now we are enabling the system also on image analysis. So when you take pictures on construction site, from analysis of the pictures, the machine learning system can see, oh, there is a little water leak there, and it will flag it as something that it has to be done. It starts to reason. It doesn't anymore wait the system for our recipes, but it starts to reason and understand what we're doing. It can understand that there is no guardrail on this scaffolding and that it is dangerous, so it will flag that as well, just from photos. So with machine learning, instead of looking at the rear view mirror back and see what we have done wrong, we can look ahead in the future. We can predict issues. Imagine we can have a drone flying daily on the construction site and noticing real time all the problems and just putting them in the system. There's so many other things that you can imagine with machine learning. So imagine if we stayed in the old world of single CPUs, in the old world of finite computation. Your designs will stay in a box, and so will our tools. And the processes that are connected with that approach, as you saw, were directive, were dependent on calculations, on recipes. They're logical, but they're not very good. Now imagine this parallel world in which everything starts to become fluid. We will not be shipping any more finite software, finished software, but our software, our tools will start to talk to each other. They will start learning from each other, and we will never finish software. It will evolve, and so will your products. And the processes now change from directive to adaptive, from rigid to fluid, from a recipe to reasoning. The tools tomorrow will be your assistants, will be your collaborators, and they will not only help you execute designs, but make better exploration of designs. The sum of all these parts results in something much grander, and this, we believe, will change forever the future of making things. Thank you.
Thank you very much, Ms. Tatjana.